applications of timber use, sort of plywood stress skin elements and three-dimensional glue laminated timber. But so Matthew's sort of talking from an engineering point of view, but with Anthony focusing on the Baggy House, his project in Devon, which some of you may have seen. It's been quite widely exhibited this year because it won the Royal Fine Arts Commission Award for Building of the Year. So they're going to be using that project as a sort of living architectural example of the sort of things that we're discussing tonight in the technical lecture. So I'll hand it over to Matthew Wells, and thank you both for coming. Okay.
Thank you. When Tim McFarlane organised this course, it fell to us to talk about timber engineering. I don't come here particularly as a sort of apologist for timber or to try and advertise its use. We are just structural engineers practicing with all the materials. Timber is one that I particularly enjoy, and it seems to me if you just take solid timber elements as being relatively simple and straightforward, there are two areas which are particularly interesting, which we've dabbled in, and which appear in Baggy House, which Anthony will describe a bit later. On the one hand, there's plywood stress skins, and on the other hand, glue lam timbers. About 15 years ago, the Swedish Timber Council, who were responsible for the development of all their materials in their country, they realised that glue lams perhaps rather played out. There's been a lot of research in building up large timber elements out of obviously a material which is restricted in its overall size. They realised that the glue lam, if you like, was not the future for them, that the future lay with board products, plywoods and particle boards. And they started looking around for ways of using plywood products. Now, obviously they studied its application, but they also began to look at ways of designing with it simply, the simple design methods which are sort of accessible to engineers, because that's the access to the actual way you can design with it is absolutely fundamental to its sort of take-up. And they came up with a method for designing stress skin wooden floors and roof decks, floors made with ply stress skins are light and very shallow in depth. So this evening's talk is about that specific development and the way we've taken it and tried to use it, and then a bit about the other side, if you like, glue lam timbers, and the way we've used those. And as I said, we've got the example of Baggy House is particularly pertinent because both appear as part of, if you like, the architectural outcome. So, plywood structures to start with. The basis of a ply stress skin is really very simple. You're actually using the surface of the member as the main load-bearing element. That slide on the right, there's a top and bottom skin, which is, if you like, the main stressed element. And in between the two is a dividing component. In this case, it's a bent glue lam timber. It can be a solid core. Ordinarily, it's just a solid timber element. It's glue lam in this case, obviously because of the curve. This example is, we've used plywood stress skin floors for a considerable period of time, and this, if you like, was our first departure from it. This is a roof designed by my partner at the time, Bob Barton. You probably know it. It's Lancaster Road by Monk and Becker Marshall, about 7 or 8 years ago. It's just a very typical application of plywood stress skins. It's basically the rules just taken to the nth degree. And what we were looking for, or what Bob was looking for at the time, was a very, very attenuated roof that would appear to float above the building. So the architectural concepts of is to terminate the top of the building. what's most interesting about it is it looks like it's a catenary, like it's suspended there from side to side. It's not. Because the architect was very keen on achieving a complete clear story all round the building, these abutments had to stay very light. If you hang a catenary across a building, you need very heavy abutments to deal with these lateral loads that will come out of the shell. Those are very light little pin joints. This is actually, appears to be a catenary, it's just a slab. It could be flat, it could be going up and down, it's just a bent slab. Just a typical detail of the way such things come, because they are particularly dependent on the way they're fabricated. You will prefabricate them as much as possible. They only just about become viable if they're made in a factory. If you try to make them on site, the site nailing and the complexity of laminating them with glue tends to sort of just tip them over the balance of economy. The one major piece of interest about this roof is because it's so thin, it's way beyond the standard design criteria. It deflects a lot, and it has this odd clear story detail, which is a sliding joint, so that the roof actually flaps up and down, 30 millimeters up and 30 millimeters down, and if you like, it just slides on that glass. There's nothing new about plywood stress skins, as you'll probably appreciate. There's a very famous example. The image on the right is a man gluing up for the Mosquito, the very famous light wooden aircraft, Second World War, and this thing on the left is Lancaster Road. But it was at that time, just in the war and after the war, that the actual glue technology was developed to enable you to use very, very light floors of this kind. It's all about the glue, not so much the plywood. Plywood can be relatively crude, but the resorcinol formaldehydes that you would use on such a highly stressed object were designed at that time. I mean, the Mosquito is always a famous example, but de Havilland made quite a large passenger aircraft. This was our next study, application of the material. This was the prize-winning East Midlands Arts Centre. Again, you can see there's a much bigger roof now. Points of interest are the roof has now just taken that free form that I was talking about, any shape you like, if you like. Same standard details to try to attenuate the edge. Alas, that wasn't built. We started looking at plywood box columns on the face of the building. Well, those columns are also stress ply in the same way. Just going back one, at the time Lancaster Road was designed, we were not aware of the main problem to do with these kinds of roof. We worked out there wouldn't be. Lancaster Road has actually got a solid core of insulation. We worked out there wouldn't be any condensation in the cavity, in the closed cavity, which is always critical with anything with a cavity in it. But we weren't aware of the major problem, which is to do, there's obviously a moisture gradient across a roof like this. If it's made of timber, the moisture content of the air not only affects the timber's size stability, which we'll talk about a bit later, but also its strength. Green timber straight from a tree is obviously much weaker than nice seasoned timber, and you will find in a roof like that the moisture content varies across the roof. And there was a major failure in Germany to do with the fact that timber doesn't actually run water or drip water, but the actual moisture content in the material is changing across that envelope. And can vary the strength of the timber. This was a little project, quite a small roof, but one where we learnt a great deal about timber stress skins. This is the housing office at Galleon House in the Isle of Dogs by Proctor Matthews. Obviously it's a double curved surface. It took us another level of complexity from the first. It's double diagonal planked. That's an image out of my boat modelling book, and that's how we did it. To get that double curved surface, we diagonally planked it in two different directions. The top surface is a Sana membrane. You'll see on these roofs as we go along there are several different ways of actually finishing a structure like this. We really wanted to do this with just a resin coat, like a boat, but the client wouldn't let us. This is a Sana membrane, like Lancaster roads. You have an unbonded membrane. The point about these roofs is they do tend to move a lot, so to avoid the strain on the surface, or straining the actual surface, that's a single layer membrane, we tend to debond it on those, I don't know what you'd call them, those strakes.
So can you explain this diagram on the right?
Yeah, this diagram on the right is, if you like, a way of getting a, that's not a very good image actually, but a way of getting a double curved surface using a flat sheet. So rather, if you like, use this again. This is obviously curving this way and across its length. You can't make a board, on the other examples, the boards are just bent in one direction, which is fine. You can sort of spray them with water, get them to bend. This is bending in two directions. To get an approximation to that, on the diagonal, you lay boarding. That's a pretty, you obviously get a facet in that direction, you lay the boarding in that direction. And you get a full lap, therefore, and you get a material which is acting in a homogeneous manner. They make boats like that in the Mediterranean still. I saw one in Greece. You can still sort of see them. On the Norfolk Broad, you sometimes see the boards grinning through in that way. That's how we did that particular roof. There's just some more details. That soffit finish was meant to be the top covering as well. And that's just how we connected the thing up. But you can see, if you like, the architectural intent of the model trying to appear in the details there. That's birch face ply. If it's got a birch face on it, you can get that kind of figuring. This is a more recent project. Not too much to say about this. This is in the RBA Journal. This is Harry Ramsden's restaurant in Cardiff. It's a stressed skin. You can see the kind of attenuation you'll achieve using that decking system. It's supported on a secondary set of glue lams. You can also see the sort of scale of a glue lam member. By laminating timber in that way, you will increase the statistical strength of the timber. Any single piece of timber will vary across a wide strength range, but by laminating it, it's almost like you become much more certain about how strong it's going to be. But it still looks quite substantial. But that was part of the intention, that you had this very light canopy against this relatively heavy substructure. It's John Lyle Architects. Right, coming on to the other use of timber, glue lams. We became interested in laminating timber in two planes in order to create three-dimensional objects. Obviously, two reasons for this. Obviously, to allow for a much wider range of form and to achieve the effects on the surface of form, this kind of figuring, where the pattern of the build-up of the timber actually comes out through the surface. And also, timber is obviously an anisotropic material. It's stronger along the grain than across the grain. But if you can laminate it in two planes or three dimensions, or laminate in two dimensions to make a three-dimensional object, you get the possibility of arranging the grains within the element to sort of suit the three-dimensional strain field. And this is the first exercise we did in that. This is a bridge by Peter Clash. It was the Swedish Timber Council award winner 3 years ago. It's a bridge. Obviously it curves on plan. It's the basic architectural intent as it crosses the water at Leith. Within that, we adjusted the cross-section. Some of the architectural ideas, but the cross-section is this asymmetrical section to suit that profile, that plan profile. And we began looking at ways of trying to, if you like, arrange simple laminated arches or ribs into a three-dimensional build-up, a sort of bread and butter build-up. Again, it's the boat modelling book, if you like. Here we are looking at the way it would work. These are just details, the architects and ours, just faxes in a competition. One of the fundamental things about timber, always to remember, it's relatively weak, and at the joints have to be spread out. It's basically spreading out. That detail down there, that sketch is just a way of actually fixing these elements together. The bridge was, I think it was 40 odd metres long. It came in 3 sections. And these are meant to represent lap plates. All the time you're going from the weak timber to the strong steel. So these are actually these leaf springs are spreading the load between each other from the timber into the main pile. These are obviously all flexible, and taken as a group they can divide the load up between them like a sort of leaf spring. Right, I'll just hand over now to Anthony to describe the application of some of those ideas in a specific project.
Okay, what I thought I would like to do is to show the context of the use of the timber in terms of this specific building, the project which we completed last year in North Devon. We finished it in November, and I think, it is actually quite it's a very complicated building, and it uses a number of different structures, timber being one of them. So immediately you can see that there are two very, very different faces to the building. One which is on the right-hand side, unfortunately it's the wrong way around, but it seems to be mine. One on the right-hand side which is facing to the south and west, which is kind of much more open, and basically everything you see on that facade is constructed of timber, whereas to the north and to the east, sort of embedded into the hillside, is a much more kind of, you might call it more traditional kind of form of building, which sort of which is all constructed of masonry, and that's the timber bit there. This is a bit of a disaster because these are actually up there. The building is actually built into the rising ground behind, which is here. This is sort of a hill, not very high hill, with the sea out here. As I said before, the masonry bit is sort of nestles into the rising ground, and then the main bit of the house, the main living areas, the living room in the centre, dining room here, and kind of a terrace here looks out towards the sea, towards the cliffs, and towards the sea down to the south. There's a coastal path which runs along the front of the whole of the building along here, and this is the canopy which Matthew sort of talked about. This is the stress-gained plywood canopy which faces west and south, with the pitch roofs on the north. The reason for actually kind of choosing these materials were sort of for a number of reasons. First of all, to do with the site being kind of having views to the south and the west, and therefore wanting to have large open areas to the major views to the north, to the south and the west. Whereas to this end of the building, that's rising ground, and therefore we wanted smaller openings, and there were no views. So that kind of suggested that two constructions would be appropriate. Masonry, as I said, blockwork to the rear, and timber and steel to the south and the west front. In this slide, you can see during construction the skeleton of the building going up, and you can see very clearly the masonry at the back here actually pushing through the timber frame at the front here, and the canopy is just around the corner there, with the chimney stack and masonry here. So that gives you kind of a sort of an idea of how, of the kind of why, from a structural point of view, we chose these different systems. From an environmental point of view, we wanted to have a kind of very, very large thermal mass at the rear, and it's all underfloor heated. So we wanted a building which would, in the summer, in the winter, would be at a constant temperature and retain heat, any heat we should put in it. In the summer, the obverse, to actually kind of have a incredible cold sort of thermal mass. So, and especially in this summer, it was absolutely amazing. It kept the house at the back here very, very cool, where all the bedrooms are. Whereas at the kind of on the kind of leading edge, on the south and the west side, we wanted an incredibly responsive building, which would adapt, which you could adapt, which when you're living in it could adapt to kind of the different, sun coming out, summer, being able to live outside. Subsequently, we have this kind of this huge wall here which disappears into the ground, and it was a very much more adaptable and lightweight structure. It also kind of reflected the kind of aspirations of the clients, in the sense that two clients, one very extrovert, kind of wanting to be kind of out in the middle of the sea almost, but really wanting just to be on the edge of it, looking at the sea. And the other, perhaps a little bit more introverted, wanting to be a little more secluded and kind of sitting kind of in the kind of depth of the building. And so for all these kind of reasons, kind of the architectural intent, kind of all these different kind of, perhaps what may have seemed conflicting in the beginning, all came together to inform the way the materials, the structure, and the kind of orientation of the building would work. Sorry. The house itself, the major elements of the building are, as I said, there's the canopy here, there's the timber frame top story, which sits above the canopy. That kind of is where all the guest rooms, all the guest bedrooms occur, whereas there's a main living platform below that, which is the main living room here, and then there's a dining room here, and a sort of terrace out here, with the kind of bulk of the building, the kind of all the domestic kind of bedrooms and stuff to the rear, to the north and to the east. The elements which we're particularly interested in this discussion, obviously the canopy here, and this column here. Throughout the house, other than the form and the kind of the placing of rooms and elements, the actual materials also reflect their kind of location in the building. I thought it would be quite good to do a quick tour around the kind of outside of the house, just to kind of get, just to illustrate the kind of what's happening. This is the house sitting in the kind of on the edge of the cliffs. This kind of amazingly kind of rugged kind of not quite granite but shaly kind of rock which sits on the edge of the Atlantic's out here, and the hill behind here. And this is the east elevation, which this is almost the dividing line. This is a timber frame, and this is timber frame here, and then this is masonry here. So you can see the kind of the larger scale openings compared to the smaller scale openings here. The masonry building is actually has much the smaller windows, and is all covered. Well, both masonry and timber is covered in an external insulation. It's not cavity construction. It's just a 70 mil of insulation which sits over the top of the structure. The house is approached. This is the coastal path along here. The house is a sort of pedestrian entrance here. This is the south elevation, which you can see here, along here. These are the windows. There's the canopy. Those are the windows, big vertical glazed windows, which slide into the ground here. And this is the timber constructed. As you move round to the west elevation, you can see here again the transition between the kind of lightweight structure, which is then kind of embraced by the heavyweight masonry construction here, and the canopy overlooking out towards the sea, and that's the main living space in the interior here. And this is, again, this is a timber frame construction above. And then as it kind of, as you move around the house, on the west, on the north and east side, the house basically eats its way into the rising ground behind, and nestles into the rising landscape. Now, perhaps we should get these. I don't know whether it's possible to. Well, no, perhaps I can. I'll have to illustrate this. The canopy we wanted as a kind of on the west and the south side. We wanted the canopy as a floating structure, because the whole idea of this part of the house was we wanted to get a sense of living outside. We wanted these elements to feel, all the elements within the space, to feel as though they were kind of within a landscape. And so they're all separated from each other in distinction, in contrast with the kind of the bedroom end of the house, which we'll see later, which has very much more enclosed and more conventional types of rooms. The actual canopy, so we've got the canopy here, which is kind of separated from the sort of timber frame structure by this piece of this frameless glass here, which runs around here. There's a light shelf here, which is aluminium, which spans as sort of an L shape, which is also free floating, which bounces sunlight back into the back of this very deep living room space here. And on the underside is artificial lighting. There's a sliding vertical wall which drops into this big trench here. And there's one column here, which the column which we're talking about in a bit more detail later, which holds up the two sides of the sort of ceiling to this main living space. The canopy had to actually kind of incorporate a number of it had to do a lot of things actually on this project. First of all, it had to form a recess for the sliding screens to come up against. It also had to include a security shutter, which is kind of eats into the meat of the construction. All these things gave Matthew, I think, made the task of designing this thing considerably more difficult. The way that it's insulated on the inside, on the inside of the above the inner layer of the plywood, and so we have to ventilate the space through an eave slot here, back and out here. The vapor barrier to stop any moisture from the interior moving into the interior of the construction is formed by this copper sheeting, which is, although it's riveted through into the plywood, actually there are neoprene gaskets along each of those joints. So that seals, so that forms the kind of vapor barrier between the kind of the interior space and the kind of into the void of the building, of the construction here. The reasons for actually then cladding it in this material, in the copper here, this is pre-patinated copper, and on the top side is stainless steel. It's an incredibly exposed environment, and the kind of thought of, we actually kind of we decided not to leave it as timber. So we wanted to use this as this copper as a sort of with an artificial history. So it's got this notion that, if you'd left it there for 10 years, the bit at which was exposed would have patinated, gone green itself, but the interior would have just been left kind of the copper colour. And so we wanted to, we had this pre-patinated to this verdigris colour in Germany. So again, reinforcing the notion that this is an external, idea this is an external space, which it is when this wall here disappears into the ground. As I said, the top of the canopy is clad in stainless steel, and again, the idea behind this was, you can use a number of different materials, but it could have been lead, could have been zinc or whatever. But what we wanted is a lightweight material. We also wanted a material which would have a reflective surface, so that there's a kind of, when you're up in the space above here, there's this sense of floating above the sea and above the building, very much in the way you'd feel you're floating above the sea here, with the ripples of the stainless steel kind of reflecting the ripple-like nature of the sea out here. And in contrast to this, you can see along the, or you just about see along the edge here, this pre-patinated copper there. Here we have the corner of the building. This one with the windows, the corner window, not only the end window here. I mean, this window, both this window and this window go down into this void below, and here it is down. And this is a kind of little corner room which kind of takes out, when we go around in the interior of the building, it takes out, it sort of frames the views to the south and the west. There's a porthole here which obviously doesn't really let in any, and there's enough natural light here, but what it does is actually gives a sense of the depth of the canopy itself. I'll let Matthew tell you about the actual kind of detail of the construction of the canopy. But what we always had the intention, right early on, that the thing should be constructed of a lightweight material. So it was a bit of a horror when my QS came to me and said, I'm afraid not. This is going to be much more expensive if you do it like this. We ought to build it on site. And it threw both me and Matthew into complete kind of tizzy, because we were both convinced that it was the best thing to do, because not only could we have it manufactured undercover in a workshop, and control all the joints and control all the gluing, but also it seemed to make sense from program. But there was a kind of there were three very critical phases in the actual building of this building, and that was one of the ones which kind of caused a lot of concern. In the end, Matthew through his previous experience, so we contacted a number of people, boat builders, because it seemed a sensible idea to use boat builders since this was being constructed in the winter, and that's kind of a light season for them. He also talked to people who'd done the roof for the Monk and Becker Marshall building, but they were in France, and the prices were coming back at very, very expensive. And at last we kind of went to the person who actually was intending to make the column, the glulam column, and he said that he would do it. And he took it on board. And we had big problems. It would have been nice also to have made the whole thing as one or two pieces, which would be joined at the mitre. But because of problems with lorries getting stuck in the narrow lanes up to the building, we actually had to it had to be subdivided into smaller elements. And it was also a question. So we had this compromise between how big they could be and how many loads, lorry loads would actually we need to take the thing to site from Oakhampton, which is actually in Cornwall, which is about 2 hours away. It was like the Monk and Becker Marshall scheme. It was craned in onto site, onto some pre-made saddles, which are kind of just curved saddles, which it just sits on, and and that went all pretty well, despite the fact that we had gale force 8 winds at the time. I'll conclude here and let Matthew take you through some more of the technical details, and then I'll come back again and talk a little bit more about the interior and the materials we used for the columns.
Okay, just a few additional points then on this roof in the context of the other examples. It did, again, take it another stage further. That image on the right is it in all its components, the way it was made. And again, going back to my little boat modelling book, it's an egg crate. Now all the internal ribs have actually just become plywood members themselves and are fixed together with sort of resin fillets. I was going to talk a bit about glues, but I don't think I'll bore you with that too much, except to say the really interesting thing about timber engineering in general terms is a sort of the wide variety of materials you're confronted with and the widely varying behaviours. There's no perfect timber to use. It may sound obvious, but all the characteristics of timber vary, and European whitewoods are good for certain things and not good for others. The glues that timbers are stuck together with are good in certain cases and not good in others. The basic frames you see on the right-hand side were stuck together with resorcinol formaldehydes, which are the glue I mentioned before, the high-strength, high-performance glues that came with wooden aircrafts during the war. They need factory conditions. They are very unforgiving if it's too cold or too wet. However, they will work afterwards in wet conditions, and they are extremely strong. You'll break the timber before you'll break the glue joint. So we use that for the basic framing of the parts that were made in the factory, on the basis that if there was any potential condensation problems in those boxes, that's what we'd use. The laps, sorry, let's just go back. The laps, those floating bits on the right hand side, are the main joints in the deck of the roof. Because of the tolerances on a roof like that, resorcinol formaldehydes don't like big gaps between the various elements. So we used casing glues there. They are the sort of animal bone glues. They're the sort of glues that you stick bits of paper together with. They're relatively weak, but they are extremely forgiving. They'll fill up all sorts of gaps, and they don't really mind what temperature it is to cure at, and so on. And it's this kind of fluency in knowing right across the range what the various parts are good for that I actually quite enjoy in timber engineering. The plywood used in those boxes in the internal frames is entirely different from the plywood skinning. The plywood inside is what they call Russian CDX, which is a very cheap ply, and the covers are a very high quality birch ply, again for different characteristics. This is just a thing in the shop being made. That's about half the frame on the right. This just sort of shows the level of technology of timber engineering in general. It's very difficult to get, if you like, sophisticated conditions in an industry which doesn't. The reason this was so, or not the reason this was so expensive, the reason there was a lot of problems with getting this costed right, because after all it is only 2 skins of ply with a lot of plywood in the middle. So if you were making this roof with steel, you'd still have to have the plywood in and out. It's to do with uncertainty. Whenever you're actually extending a contractor beyond a degree of certainty, the risk involved has a cost penalty. That slide on the left does just indicate that timber is quite forgiving, if you like, and is a very easy thing to use. The last conversation I had with a Swedish timber engineer, he actually claimed that timber actually keeps workmen happy and you get better work without any problem, because it's just a joy to use. And I think there is a degree of truth in that. I have found that joiners will do more than steel fabricators will do at a very crude level. Right, back to the house for a bit. Back to the house in a minute. We'll just walk around the house and then concentrate on this timber column, which is a key feature of both the architecture and our first application of laminating timber in 2 planes.
Okay, well, I suppose a good place to start is the front door, and so this is actually the entrance door is actually on the northeast corner, which hides you from all the views of the sea. So it's kind of we're sort of almost in the sort of the dense bit of the house immediately here, and the idea is to kind of to make the whole thing a surprise. You arrive. Actually, could I have this one? turn this one around. You arrive at ground floor level on the one on the left. Is it possible to turn that one round again? You arrive at the here, as I said, which is the front door, and that sort of is around the back from the main bit of the house. And what we're going to do is going to take a tour, walk into the entrance hall, and then you spiral up the staircase up to the top, to the floor above this, the playroom. Great. And you come up the stairs, and there's the main living room, which is in the centre of the house, which overlooks the dining room to the south and across the terrace to the west here. The section is quite complicated, so that this dining room appears twice on both floors. But you come back down from the living room to the dining room, and then underneath this room to the kitchen here. And so this is one of the kind of main important things about the house, was it was supposed to be a kind of very, very strong social organism, where the clients could kind of converse, talk, disappear, but all everybody can be aware or partly aware of each other. And then if we come back from the living room, we come down the spine here to the kind of main domestic rooms, the main bedrooms here, with the main bedroom and the master bathroom back here. And if you come back along this route here, you go up a glass staircase which takes you to the top floor to the guest bedrooms. So basically it's a kind of a central ventilation routes occur. This one here, another one through here, and another one along here, and spiralling around the main space. As I said before, this is the section. So the main living space is here. The kitchen has a kind of relationship with the main living room, so you can chat when cooking and everything. And then there's a playroom here, and the main dining room is at this level, which is up here. Guest bedrooms are up here and here, looking across the sea, and there's a view, and there's a little porthole from this bedroom back into the living room here behind the staircase. As I mentioned before, the story of the house is very much to do with the changing materials. Back at the rear here, very much more rougher. Here there's a granite column, and as you move through the building, the materials start quite rough and large scale. This is a monolithic piece of granite which I found in Dartmoor, and we just got brought to the site. And then you come up the staircase, and then there's smooth polished slate here, and then it moves into timber here. And then on this side of the house, we talked about the canopy, but then there's this much more refined timber column, which is kind of in both texture, form, construction, is kind of the reverse of the granite column. So you arrive in the hallway, and you're greeted by this kind of piece of granite. And it kind of, when you first arrive in the house, it kind of it's pretty strange. And it supports this kind of rather grey English sky, which is lead. It's a lead-covered plywood panels. It's actually supposed to be originally sacrificial shuttering. Matthew and I were trying to design a kind of a steel shuttering, which would then have a concrete slab put on top of it. But unfortunately, we ran out of time, and they just had to cast the concrete slab conventionally on a timber formwork shuttering, and we had to apply this as a sort of a thing right at the end. The staircase takes you up to the main floor level, and on the half landing there's this kind of this loo, a guest loo here, which takes you, and then in the distance you can see the kind of main room. And this is at the back of the house. This is the main bathroom, just kind of this sort of obverse of the kind of forms that we see in the front of the house, which buries itself into the ground, and the ground levels are about up here. We then kind of coming back down from this is the living room up here. We've come down from the living room. This is the kitchen, and there's the glass staircase which takes you up. I mean, as I said, the materials get literally lighter as they get up to up to the main top floor. And this is the glass staircase looking back down into the kitchen. The glass is cast. It was cast in Hackney, and it's supported off these. It's sort of, again, it's a development Matthew's done on Yves Jerichner's kind of staircases. But what I wanted here was something much more, in a sense, more cruder. It's just acrylic is embedded in these rendered walls on little angles, which you can't see. And these L-shaped glass treads just sit on top of the acrylic. And it's kind of got, and there are sandblasters so you don't slip. And it has this kind of marble, sort of translucent marble feel to it. Both the main guest rooms take you out onto terraces which overlook the sea. Now, coming back to the living room, as you enter, you come on the landing at the top of the staircase, and the first view is framed by these a series of horizontals, which is the column, the canopy here, the light shelf here, and the kind of the framework to the big sliding screens, and then that's kind of counterpointed by this vertical column. What we wanted to do was to create this kind of sense of a belvedere, which overlooks the kind of the column, which overlooks the sea. Here is the column sits right in the middle of, this is a solid masonry kind of arm which encloses, which separates the kind of lightweight structure from the kind of heavyweight bedroom wing here. And this is the kind of little corner room which also frames the view down here and the view here. And the column sits actually absolutely dead in the middle of that, although in spatially it feels as though it's kind of on the edge. The notion was, it's something that, a lot of sort of, when you travel, you see kind of things which you think are pretty extraordinary. This is the Tala in Isfahan, in the main square in Isfahan. And it was amazed me, these extraordinary elongated columns with these kind of, just sort of seeing the whole thing as defying gravity with this kind of whole, the soffit sort of floating above it. And it's a sense that this is the sense that I wanted to achieve with this kind of, with this main living space. The column, as I said, this is this drum which takes out the corner views. This is with the window down on the left-hand side, looking out to the south, and this is a fixed window to the west. And then there's another corner window, as we saw earlier, which is the other side of this. And just a sketch, just trying to explore the relationship of column, ceiling, and kind of canopy. Now, the whole business of, as I said, I wanted to contrast the kind of these are two only columns that appear in the building. Contrast the kind of the much more kind of highly engineered, what seemed to me highly engineered south face of the building, with a kind of with the north, which is much more monolithic. Even this, I thought this column here, the granite column, was kind of, I just thought we'd put it in, and Matthew said, no, you can't just put it in. Although granite is a very strong material, there are natural flaws in the material, and there's a sort of scenario where you could have put it in, loaded this thing because it supports a big chimney above here, and the whole thing could have collapsed. So what we had to do is we had to drill and put a little spigot in here just to make sure the strength of the granite had no flaws in that part of it. There's the kind of things that an architect, I guess, doesn't really think about until he's talked to his engineer. Whereas this column here is kind of the inverse in the shape. It's completely the opposite to this. The idea was to defy gravity, to kind of put the kind of visual weight at the top. From a structural point of view, this obviously kind of, could then, because of bending, it needs the biggest depth across it here. It could actually kind of have come in here and tapered it back in here. But it was completely, what I wanted was something which was sort of like top heavy. Also, I wanted something which visibly didn't sort of touch the ceiling or the floor. So it's separated, it's sort of elevated by a kind of by a spigot here on a brass plate, and a brass plate here as well, which is again different. So the junction is hidden, whereas it's not hidden there at all. There are other ways we looked at other ways of kind of constructing this column. But what I was, in terms of strips, you can't really see it, but one option was to make it out of strips of rock maple, which is the material the column's made out of, so it was so it became like a hollow barrel. But what we came up with was this really nice construction, which is solid pieces of maple, which are X 2x2 50 by 50, which are planed down and glued together. And in cross section, that forms a kind of grid of rock maple, which in a way is the kind of the way the house was. The house is very much laid on a grid, so it's like a microcosm of the house. But what's even more wonderful is the way when you cut through the form a conic out of it, the shape out of it, you're cutting through those sections in a very, very elongated way. And so you get this fantastic pattern there on the kind of side of the column, and you can just about see these sort of hyperbolas kind of wrapping, coming down the side of the column. It'll be clearer in some slides that Matthew will show later on. We had big problems procuring this thing. For people who originally were going to do it, just bottled out. I think they were just terrified about doing it. The contractor said, absolutely, we don't think this is a very good idea. I went back to Matthew and he said, look, I've got all these people who have been very, very kind of negative about this thing. And they said it's going to crack up and all the rest of it. Well, the first thing we decided to do was to build a temporary brick column on just beside it. So when the house was being built, we would reduce the kind of damage and also movement in the timber. But more importantly, Matthew kind of devised this because a system of artificial shakes. Because if you just got a piece of timber, eventually it would all crack up, and you'd get shakes due to the movement of the timber. And what he developed was an internal to actually create these artificial shakes within the actual thickness of the timber itself. So there are actually these. Well, I mean, I think the best thing to do for me is to let Matthew talk about it, because he's actually got some slides showing the details through the column, which actually kind of indicate that. Once we'd actually found somebody to do it, in the end, they couldn't actually kind of turn the column because they hadn't got a lathe long enough. And there were discussions about, making a temporary lathe, setting it up in a car park. But again, we've long after kind of a lot of kind of hassle and difficulties, we found, Matthew actually found that the centre of the organ pipe business is in Bideford, which is only a quarter of an hour away. And this is the centre of the organ pipe in Britain. And it's one of those fortuitous things that they said, yeah, well, we can turn it. And they turned it. And it came out beautifully, except for one little problem, is that we hadn't actually realised that by planing the timber down initially to get from the 50 by 50 sections to 45 by 45, it meant to reduce everything and reduce the length of the whole made the whole thing much narrower. And we had some gaps in the column, here and here, and then they had to mask these, put in little bits of timber and cut it in. And I mean, it's kind of now it's really lovely, because it's kind of now it's a memory of the kind of the horrors that we went through when we actually kind of commissioned and got the thing put together. I think what I'll now do is I'll hand back to Matthew and let him tell you a little bit more about the technical detail.
Okay, we've been talking for an hour, so I'll just canter through this next bit, and if anybody wants to pick up on anything at the end. Oh, I lost one. Right. that's the column during the construction phase, just as it was going in. I thought that slide on the left actually showed the brick pier in, but in fact it has been removed. It carries about 14 tons, which is about 1/4 of that house, 1/4 of the upper floors of the house. Because it's timber, what I really wanted to just finish off on was talking about the moisture movement problems in timber. If you're going to build up something in 3 dimensions in glulam, there are a lot of problems with cross-grain shrinkage. If you look at something like a cheese board, if it's an old one, and we've got an old one in our house, it's extraordinary that the way they go elliptical with the if you like, continually being washed, the cross-grain shrinkage is 3 or 4 times as high as the longitudinal shrinkage. That's to do with the shakes, but we put this in right at the end of the job to avoid the drying out moisture changes in the house, and we jacked it up on that thread there. So there's a great big spanner went on that, and we just lifted the house basically until it actually came off its brick pier. Actually, a contractor in London taught me this trick. The first time I ever did this, put a column in underneath a building. I thought you had to sort of strain gauge it and so on, but he just taught me that if you just jam a piece of wood up underneath the building, then you can just jack it away until the wood falls out, and that means you're about to lift the building up, which is just the point where it becomes dangerous, obviously. Yeah, but we were doing, at the same time as we were doing Baggy House, we were looking at this job. This is an Eva Jerichner job I just throw in. It's made of rock maple, which is what the column at Baggy is made of. The treads are, at least. The newel is obviously steel. It's made in this country and transported to America. This country is considerably damper than North America, and those treads were going to move 3 or 4 millimetres together, which seemed quite an extraordinary amount. And so we put soft joints in between each of the risers and the treads. It does need a joint, a load-carrying joint between each one, because obviously it cantilevers forward and then carries the glass. Carries the glass balustrade all on the outside, but in there there's a little rubber joint so that this lot can move this way and up and down to a certain extent. We didn't do it. That's one way of dealing with moisture movements, as the moisture swings back and forward. We did it another way. These artificial shakes that Anthony's referred to. That's the column. That's a rather fanciful drawing of the figuring. It doesn't come out like that. That shows diamonds. In fact, it comes out as this sort of parabola, almost like a candle melting. Down the middle, cotton interlayer, the kind of thing you have in the lapel of a jacket. The moisture's got to be allowed to go in and out of this column so that the whole thing moves together. It's obviously full of glue lines, and moist vapour won't really cross those glue lines. So it's got this sort of test card of artificial shakes in it, which is, if you like, allowing the vapour to move around freely inside that object. It doesn't really, I mean, it matters, but it's not really critical to the structure. If you go for a drink in a Cotswold pub, you'll see that most of the timber there has a lot of shakes in. That's because they used to work it green, because oak is extremely difficult to work anyway, and with just mild iron tools, it's very hard. But anyway, shakes are not a particular problem longitudinally, but they show. So we put them on the inside, so if this does move differentially across itself, it can do, but also to keep it all moving about the same. Just a couple of concluding remarks then. Obviously, timber is a renewable resource with an extremely long tradition of use, and it must have an important future. We've shown you a couple of different applications tonight and tried to show you how the architectural intent is expressed in that application. There are obviously going to be considerable future developments in its use. As a natural material, it's subject to the transformations that you can achieve with bioengineering. Toyota are already trying to make a tree that will swallow pollutants, but it must be possible, therefore, to enhance its material characteristics. We as engineers, obviously in the shorter term, are just concentrating on bigger and bigger applications. We're working on a roof at the moment, which I can't show you, which is a large roof for an entire house for future systems. And I think the main development with plywood skins will be the web detail that you've seen transform itself through those examples, from glue lams to solid cores, to this egg box construction. There will be a different form of a web. We haven't quite got that right yet. We'll be using either a solid core of a different kind or some kind of Warren Truss core. There's still much to resolve in the application of three-dimensional glue lams. These are rather Heath Robertsonish ways of dealing with the moisture movements, and there's a lot to learn about the behaviour of different timbers, because obviously different timbers brought into contact with each other behave in different ways. We would like to be able to, if you like, develop this figuring using different species, but they all have different characteristics, and the kind of forces developed by moisture movement are far too great for glues to deal with, so they've actually got to be controlled in some way. Once this three-dimensional laminating becomes everyday and fully possible, then there's if you like, a complete study to be done of the generic forms that are possible with this material, and I expect that will be done through more examples in the future. Thank you.
Thanks for that talk. We'll be up in the bar, so if you want to ask any questions, you can ask it up there. But there's some great notes that Matthew's done that have got some of those details in it. There's not many circulating, so you can get them from Belinda. Okay, the master copy lives with her, so get hold of it, and it's got some reading references and things on it. So thanks again for that talk, guys.